Final day of the workshop, and we're very happy to start today with a lecture by Ferrari on phases of matrix, quantum mechanics, and quantum gravitational collapse from the new large unit.
Okay, thank you everybody for attending the seminar. Thank you the organizers for allowing me to come, and in particular to realize these old dreams that I had to see these animals in their natural habitat. So this was one of the climax of the conference on top of all the very good scientific talks we had and discussions. My title is slightly misleading. I kept the one I originally intended to cover, and I will actually cover this, but I added as well the first part, the first half, on tensor technology, so that you can have a better maybe understanding of some of the underlying techniques that allow you to do these sort of things, at least partially. So the plan, really you have two parts. This is the matrix tensor or tensor model technology as explained in this paper with Vincent Rivasseau from Orsay and Guillaume Valette, which is one of my PhD students in Brussels. So the main reference is this paper, but you can also have a look at two other related papers. And then the second part will be more on the physics and some new physical results that we have obtained in this class of models, which could be actually could realize a quantum description of the phenomenon of gravitational collapse. Okay, so I will explain this, and that's a PRL that we published in July, but there are much more work in progress now, so more papers should appear on that subject. Okay, so let's start with a few important graph theoretic ideas. Some simple, but maybe that in a way that these are things that you probably know, but maybe I will present them in a way that is new. So, of course, a graph, Fineman graph, for example, is just a set of vertices and edges relating to vertices a priori. But we're used to draw the graphs on a piece of paper or on a surface. That's how we represent them. When you draw a graph on a piece of paper, maybe without even realizing it, you're actually adding a lot more information to the graph than just the vertex and edge content. Indeed, as soon as you draw the vertex on a piece of paper, you choose automatically a cyclic ordering of the lines that are incident to each particular vertex you're using. So, this would be, for example, a quartic vertex in some field theory with a phi 1, phi 2, phi 3, phi 4 interaction. You can draw it in this way, but of course you could also draw it in this way, because phi 1, phi 2, phi 3, phi 4 is also phi 1, phi 2, phi 4, phi 3. So there is no difference between these two guys. It's just the way you draw eventually the diagrams that will change, but the diagrams will be exactly the same. However, in the case of matrix models, so when the fields are actually matrices, the vertex in your field theory actually do contain this additional information about the cyclic ordering, because the vertices, if you choose a single trace vertex, will be now trace of some bunch of matrices, and now the trace is cyclic, has a cyclic ordering associated to it. So a vertex trace of x1, x2, x3, x4 is no longer a vertex x1, x2, x4, x3. So this additional information that you have when you draw a Fineman graph on the surface is actually relevant in the case of matrix models. And that's why there is a well-defined one-to-one relationship between Fineman graphs of matrix models and graphs drawn on surfaces. And then the genius of the surface that you obtain when you draw the graph in such a way that no two lines will intersect is what we call the genius of the Fineman graph. And this notion was introduced by Toft. So a nice way to depict all this is to use this fat graph or ribbon-like representation, but this is just a way that emphasizes the fact that the cyclic ordering is crucial, is important, okay? But you don't need this as soon as you understand that you really mean that the cyclic ordering around each vertex has a physical content. Okay. So that's actually ingredient number one. You need a second ingredient when you want to draw a graph on a surface. You have to choose the type of lines. You have two possible types of lines, plus or minus, untwisted or twisted, and this corresponds in the ribbon fat graph representation to propagators with untwisted ribbons, the standard ribbons. This would enter, for example, in Hermitian matrix models and would be associated with this kind of index contractions. Or there's also the possibility of having twisted ribbons. So it's a ribbon that you twist, and this will enter, for example, when you have real matrices. For example, in the symmetric case, you have to take into account two combinations, the two terms. So one term will be this one, but the second term will be that one, because you have permuted two indices. Okay? So cyclic ordering around vertices, type of propagators, of edges, and that gives a unique surface on which the graph is embedded. All right, any question about this basic graph theoretic idea of drawing graphs on surfaces? Okay? Okay. So another important idea comes from matrix models. So consider an action for a matrix model. All my actions will be zero-dimensional because for this discussion I only need the index structure. So it applies to field theories in any dimension, but my formula will be zero-dimensional. So consider matrix model action. Typical action is like this. The IA of x represent interaction vertices. And here I want to allow an arbitrary interaction vertex, meaning I allow multi-trace terms as well. And the TA is the number of traces in the interaction. So this is the correct Toft scaling with this particular factor of n here in the case of multi-trace matrix models. For example, this is a drawing for a double trace interaction, trace of x squared, trace of x squared. It would be a vertex like this. Fine. In a model of this sort, it's well known that any physical quantity, but for example here the free energy, has a large n expansion in powers of n to the power 2 minus 2h, where h is a positive number, given by this formula. So what is this formula? The first term is just the genus of the Fineman graph that you consider. That's the term everybody probably knows about. It's very standard. And this is the only term that enters when you have single trace matrix models. Okay? So single trace matrix model, this other guy is zero, always zero. Now, in multi-trace matrix models, you have to add this guy. What are these terms? So the TAs, as I said, are the number of traces that you have in your interaction vertices. Here you sum over all the interaction vertices in your Fineman graph. And B is the number of connected components of the Fineman graph viewed as a ribbon graph. Okay? The Fineman graph in itself is always connected. In the free energy, it's the sum of connected Fineman graph. But when you draw it in terms of ribbon graphs, it may become disconnected when you have multi-trace interactions. And this should be very clear, for example, from this example. This is one vertex, but in the ribbon graph representation, this might produce two disconnected components of the ribbon representation. So if you like, in terms of surfaces, two disconnected surfaces. So that's why you have this number B here that counts the number of connected Riemann surfaces, if you like, associated with your connected Fineman graph. And that's the H that enters the expansion. G, what is very important, of course, is that G is positive. So that's the fundamental result that allows you to define the large n expansion in general. But this other guy here is also positive. You can write it in this way. So it can be interpreted, this is some sort of topological connectedness property associated with the ribbon graph. And it can be interpreted as the number of loops in some associated abstract graph, if you like, where the abstract graph you consider is built in a very simple way. To each Riemann surface, you associate a vertex, and to each multi-trace interaction, you associate a vertex. Okay? And then so the number of vertices will be B plus the total number of original vertices like this. And then you trace, you have edges in this abstract graph that link each multi-trace interaction to the Riemann surface they belong to. So this gives an abstract graph that you can draw, and it's very easy to see that this quantity is just the number of loops in this abstract graph. So that's also a positive quantity. It's always positive. So the expansion is well defined in terms of genera and this connected sort of property of the graph. Any question about these multi-trace matrix models? Okay. All right. Now, an additional important property from graph theory. So we'll call a D-bubble or D-colored graph a regular graph. So regular means that the vertices, the valency of all the vertices is the same and will be D, such that you color the edges. Okay, so each edge has a given color picked from the set from 1 to D, and in such a way that the D edges that are incident to any given vertex carry all the possible D colors. Okay? So for each vertex, you have all the possible colors attached to it, and each of them appears only one. You cannot have the same color twice, incident twice. So these sort of graphs, we call them the D-bubble or the D-colored graphs. Interaction vertices for tensors of rank R are bubbles. The idea is that in an interaction vertex, for each tensor field that appears, you associate a vertex in the colored graph. And for each index, you associate a color. And the way the edges are drawn correspond to the way you contract the indices in the interaction. So it's a very nice, very natural way to depict interaction vertices for tensor models with giving the full structure of the indices in the drawing. So for example, this sort of interaction is the so-called non-melonic and non-bipartite. I'm going to explain this in a moment. And it corresponds, if I write the interaction vertices in a matrix language, it would correspond to this interaction, trace of x mu dagger, x mu dagger. So x has two indices as a matrix, and mu is a third index. Okay, so that's like a rank-free tensor, if you like, but I wrote it in a matrix notation because it is convenient and nice for other purposes. The fact that it's non-bipartite, what does it mean? So if, you can insist, for example, of having a bipartite structure for the green and the red lines, meaning that the edges of green and red colors will always link vertices of two different types that you've chosen, like unfilled and filled. So this is bipartite for these two colors here. When it's bipartite, it means that the symmetry associated with the indices is UN, so unitary symmetry. But you have here as well the red lines, which are associated with the indices mu, which are not bipartite here. They violate the bipartite structure. That's fine, just means that the symmetry associated with this color will be orthogonal, not unitary. Okay? And we can do everything, we can do all these guys. So the graph does not need to be bipartite necessarily. This is another example corresponding to the trace of x mu dagger, x mu dagger. It's called melodic for reasons I will explain a bit later, and this one is bipartite. Okay. Now, maybe even more interesting, not only the interaction vertices of tensor models are colored graphs, but the Fineman graphs of tensor models are also colored graphs. But now, if you have tensors of rank R, the Fineman graphs are R plus 1 bubbles. The idea is very simple. The Fineman graphs are built from vertices by adding propagators. And let's just decide that the propagator lines is just another color, 0, typically. And here, the new color I have is not a new color, I just use dashed lines. Okay, the dashed line is the color 0. And by construction, automatically, when you join vertices which are R bubbles with these propagators, you build R plus 1 bubbles. So the Fineman graphs are also bubbles. Note, in parentheses, because that's a useful remark, that when you have a D bubble, you can remove all the lines of given colors, let's say P colors, and remove all these lines. This produces automatically a D minus P bubble. Good. Now we come to the fundamental ideas in this field. So one old and the other new that we introduced in our recent paper. As we say, there are many ways to draw a graph on a surface, and in particular to draw a colored graph on a surface. So there's a very natural notion associated with colored graphs, which are called jackets, and the jacket of a colored graph is a particular way of drawing it on a surface. How do you build a jacket? It's a very natural way when you have a colored graph. You just pick a cyclic permutation of the colors. This gives you how you should depict each vertices according to the cyclic permutation of the colors you've chosen. Okay, this gives you this information. Then you might have two types of vertices, field or unfield, if you like. So the field, you use the cyclic order associated with the cyclic permutation you have chosen. On the unfield, you choose the reverse order, inverse cyclic permutation. And then you decide that the lines that join the vertices are untwisted if they respect the bipartite structure that you have put forward, or twisted if they do not. This gives a rule, a unique rule, to associate to any colored graph a graph drawn on a surface, a jacket. Now, when you have a jacket, you can associate very naturally its genus. And then, when you have a colored graph, if you consider all the possible jackets together, it's very natural to define what is called the Guiraud degree, which is just the sum of the genera of all the jackets associated with the colored graph. This is the degree. Okay. It's a very crucial, fundamental notion in tensor model technology that was introduced by Guiraud for rank free, for free colored graph, and generalized in the way I just explained for bipartite graph by Rivasseau and Guiraud, and the general case we did in September, but that's a very easy generalization when you have graphs that are not necessarily bipartite. You just have to consider non-oriented surfaces. That's a trivial generalization. So this is the degree. Graphs of degree 0 are melons. So this is the mathematical definition of a melon. It's a graph of degree 0. They are, in some sense, superplanar, because when the degree is 0, since each of these genus here, of course, is positive, then it means that all the terms here are 0. It means that all the jackets are 0. In other words, a melon is a graph which is planar, whichever way you choose to draw it on a surface. So in this sense, a good alternative name is to call the melon a superplanar graph. It's planar, whatever cyclic order you choose. It's a very special structure. Okay, so that's one natural quantity associated with the colored graph. Now there's another one, which is as natural, and we'll see plays an important role, and that we introduced in our recent paper with Rivasseau and Valette. So the other way is as follows. First, you pick a particular color. That's very natural because in Fineman graphs for tensors, you always have a particular color which is singled out, which corresponds to the propagators. Okay, so let's pick this as a special color, the propagators. And then consider all the possible matrix model graphs which are embedded in the colored graph. So you keep the color 0 as the propagators, and then you pick any pair of color, I and J, matrix indices, if you like, and that's it. Okay, so you remove all the colors except 0 and I and J. This is the matrix model graph embedded in the tensor model graph. Then you have, of course, the standard Toft genus associated with this matrix model graph. Or more generally, you have this index H. actually you have to consider this generalization because the matrix model that you find from the tensor model by keeping two indices might contain multi-trace interactions. In general, it does contain multi-trace interactions. And we'll see when it does not. It's an interesting special case, but in general, it corresponds to a multi-trace matrix model. So that's why the relevant quantity is not the genus, but this generalization, which weights the power of n in the large n expansion of the matrix model. Now, you can sum all these indices hij over all possible matrix model embedded in the tensor model, and that defines what we've called the index of the graph. Okay, and it's also a positive number because we know that these h's are positive. So you have really two natural notions associated with the tensor model graph. The degree, which is the sum of the genera of all the jackets. This is all the possible ways of drawing the graph on a surface by keeping all the colors. Or the index, which is by looking at all the matrix models embedded in the tensor model, singling out two indices out of the R that you have, and doing all the possibilities and summing. That gives you another positive number, the index. Okay, any question? It's okay? So now let's consider the most general action that you might imagine. So some kinetic term and then the sum of any interaction term. So the BAs are the bubbles that represent the interaction terms. You have to decide how you scale the coupling constants to define any large n or large d limit you might have in mind. So I'm here making the distinction between n and d. So n is, I choose from the beginning two indices, if you like, in my tensor, and I decide to call them the matrix indices. And then I have little r other indices. Total number of indices is just little r plus 2. Okay, that's one way to depict the action. And then, as is well known, when you want to consider large n, large limits, the fundamental ingredient is what scaling are you going to choose for the coupling. The large n limit here is just the standard large n limit of a matrix model. So we're using the Toft scaling. An n in front, and because we can have multi-trace, here we add this n to the 1 minus t, which is the number of traces. The standard, completely standard. But we also want d to be large. So d is the range over which the other indices will vary. Okay, so all these mu indices vary from 1 to d. You might consider d equal 1, d equal n. Okay, but it's interesting to distinguish the two. So how are we going to scale this couplings? The historical coupling, so-called Boson-Guiraud-Rivasseau coupling, so that's the original theory of general theory of tensor models, is as follows. This coupling tau A is scaled according to the Guiraud degree of the interaction. So tau A is d to this power. I'm going to say what this is, but let's forget these two terms for the moment. It's d to this power times some Toft coupling mu A, and the large d limit is defined by keeping mu A fixed. So d goes to infinity, mu A is fixed. So it's the Guiraud degree of the interaction that governs the scaling. Then, okay, when you can have multi-traces, you have to add these two terms. So T of BA is, as usual, the number of traces. C of BA is the number of connected components of the tensor bubble. So the interaction bubble of the tensor model, taking into account all the colors, might be disconnected too. So we did the most general case. But you don't want to consider this full general case and restrict yourself to C equal 1 or T equal 1 or T equals C. These are the simplest ones. Okay, so the really non-trivial ingredient is this one. So for example, if you have a term like this here in your interaction, then this will scale as d to the power minus 1. For a guy like this, T equals C, and the degree is 1. Little r here is 2. So, little r here is 1, and the degree is 1/2. So, of this guy, you can compute it easily. So, you scale it with a factor 1/t. guy, the melonic guy, by definition, it's melonic. Why I called it melonic? It's because the degree of the interaction, the degree of the graph associated with the interaction is 0. So this graph is a melon. This graph is not a melon. Okay? And in melonic interactions, the degree is 0, so they don't scale with D. So the scaling is just given by, of course, this overall factor here, but then these guys do not scale with D. Then, the fundamental result proven by Bonzon, Guro, and Rivasso is that with this scaling, you get a good large N and large D limits. Well, they were doing always D equal N in their cases, but you can generalize to a large N and large D. And the Fineman graph is proportional to the usual factor of N, so that's not, oh, there should be 2 minus 2h here. So that's the standard factor. And a certain power of D, which is governed by this L. Let's forget about these complications. Again, this is when you have disconnected bubbles and so on and so forth. But in the important piece is this. So the large D or large N expansion is governed itself by the degree, but not the degree of the Fineman graph. So it's a very remarkable thing. Okay? You scale your couplings according to the degree of the interactions, and you find a large N expansion which is governed by the degree of the Fineman graph with particular scalings. Good. So this is the normal tensor model theory governed by the degree. The leading order Fineman graphs, by definition, are melons. However, this model, this class of models, this limit, is very much like a vector model. You can see it here. You know, this case as a standard vector model, this will be suppressed. It's not so interesting. In particular, at leading order, only the it's something that you can prove, it's not very hard to prove, only the melonic interaction vertex can contribute. So in this scaling, even if you introduce this interaction in your Lagrangian, at leading order, it will not contribute at all. Only this guy will contribute in a way very similar to what you find in vector models. Okay? So this is not so interesting. These graphs look very much like vector models. It's nice to see that you can generalize to tensors. That's a non-trivial statement. But the physics is very similar to the vector models. What we need for the modern results is different. And this is the new scaling that we have introduced this summer to do the full theory. And it works as follows. So this was the old Bonzon, Guro, Rivasso scaling. This is the new scaling. So essentially you get the same factors except that the minus 2 over factorial r degree is replaced by plus 2 over factorial r plus 1 degree. This new scaling is greatly enhanced compared to this one. You know, we are going to take large D at fixed lambda A. So this, the tau A, the coupling in the Lagrangian, scale with a much higher power of D than in the old scaling. You have enhanced a lot of interaction vertices. So you're going to have many more graphs, many more vertices can contribute with high power. Actually, at first, it seems sort of impossible that this could still work, because you could say, oh, we're enhancing too much now. How can you enhance a scaling? I mean, if you enhance, then you're going to build graphs a priori with arbitrarily high powers, so the large N limit will no longer exist. It's absolutely non-trivial that you can enhance, actually, the coupling, and still have a well-defined large N or large D limit, and that's one of the main results of the work we've done. So this enhancement, since of course the non-trivial piece here is proportional to the degree, is for the non-melonic interactions. For the melonic interactions, degree is 0. So the old scaling and the new scaling coincide. So this interaction is still not, goes with a 1 here. Nothing is changed. However, the non-melonic interactions, for example, this one, before was coming with a 1 over D in front. Now, in our new scaling, you put a square root of D here. It's enormously enhanced. So it will play a much stronger role in the large D, large N limits. the result is as follows. The Fineman graphs are proportional to this quantity, and the power of D is now governed by the index of the Fineman graph. So all these are the same kind of decorations that we had before due to the fact that the graphs and the bubbles might not be connected, forget it. The fundamental piece is this index. The new large N, large D expansion of tensor model is governed by the index, but this index was positive. So the expansion still exists. It's still well defined in spite of the fact that we've enhanced a lot of couplings. In the new expansion, governed by the index, so many more graphs contribute, and in particular, now the non-melonic interactions can and do contribute to leading order. So in this new limit, these vertices will appear in the leading order graphs, unlike the standard limit. So we've called the index 0 graph the generalized melons. So it's a much larger class of the ordinary melons. Ordinary melons are generalized melons, but the other way is incorrect. And so the limits of these models will be physically more interesting because it will contain many more graphs. This is the expansion we need to get SYK-like physics in general. A last comment. This construction is singling out some particular interactions that we call maximally single trace, which are the tensor interactions which are single trace, whatever matrix model you choose to write them down. Okay, so I said for any tensor interaction, you can pick two indices and write it as a matrix model interaction. The maximally single trace tensor interactions are the interactions which are single trace for all choices of the matrix model you use. This geometrically, so this is an example. Geometrically, it has the very simple interpretation that when you have a colored graph like this, pick two colors, for example, the blue and the green here. Then the number of cycles of alternating blue and green colors in the graph is always 1. Blue, green, blue, green, blue, green, blue. That's it, and you've done all, there's only 1. And whatever pair, let's say blue, red, green, red, green, red, green, red, green, red, only 1. And you can check that this is true for all pairs of colors. So graphs with these properties are the maximally single trace graphs, and they are the natural generalization of the single trace interaction terms in matrix models from this point of view. It's a fascinating class of tensor models, and an outstanding open problem is to derive the form of the generalized melons in this case. This is not known, and that's a very interesting graph theoretic problem. We've solved it for this type of graphs which are complete. In the case when the rank of the tensors is the prime number. This prime number condition comes from the fact that actually it's only when R is prime that these guys are maximally single trace. So if you generalize this sort of graph to higher ranks, it's only when the rank is prime that they're maximally single trace. And when they're not maximally single trace, the derivation of the leading graphs become extraordinarily complicated, and we've not done it. But when it's prime, you can do it. It's in the paper. It's very technical in a sense, but this can still be classified completely. In other words, models based on these sort of things can be solved. You can write the Schrödinger equations. You know what you're talking about. All right. So this is the end of the first part of my talk on tensor model technology, just to give you the overview. So if you have questions on this, I will come back on large D, etc., but more with the physics applications in mind. No question? Yeah.
So the usual Toft scaling is unique.
Yes.
So can you give us some insight why for tensor models it's not unique? Is there a simple way to see why?
No. I think this is one of the complication and subtlety associated with tensor models, which puzzles me. And this is qualitatively very different from the matrix model. What Robert wants to say, in the matrix model, if you enhance the Toft scaling, you get nonsense. The large N limit does not exist anymore. If you reduce it, of course it works, but it becomes completely trivial. So there's really only one scaling which is interesting. In tensor models, you have more scalings. A very deep question, so there's a thesis that was done by Luca Lioni in Orsay, he ended in September, devoted to this question is, for particular interactions, can we find the optimal scaling? So the one for which the large N limit still exists, but as soon as you enhance, it doesn't exist anymore. Can we find the optimal scale? And he did a few cases. It requires a lot of technology and a lot of work. You could then ask, in your new scaling, is your new scaling going to be optimal or not? For MST, for maximally single trace interactions, we've proven that it is optimal. So that's the best scaling you can do if you want to include as many graphs as possible. We have also counterexamples where our scaling, even though it's much better than the old one, is not optimal. So in the Luca Lioni work, we found actually having two vertices, very nasty one, for which the optimal scaling is actually enhanced compared to our scaling. It's not an MST, of course, but it can work. The general theory of this, general understanding, I don't know. It's completely open, and nobody understands these things. But that's a very, I think, very important question. We would like to be able, for any interaction, to find the best scaling that allows to define the larger limit. It's not known. It's not even known if the scaling will depend on the other vertices that you have in the model. Usually you pick one vertex and you want, just by looking at the vertex, decide what is the scaling. This might not be possible at all, because it might be that when you add other vertices, they can mix up and create graphs that will blow away. So it's a very complicated problem in general, but very important, and I think people are trying to understand better.
Next week. So you want to put these graphs on some Riemann surfaces?
Yeah.
Why do you need some points? What is special in this genus zero diagram?
Why is this so different from this one? That's also a good question.
No. To me, you put graph on the Riemann surfaces, but the interaction structure is different from the structure of the Riemann variance. How do you connect vertices?
So, well, this guy, if you pick the green and red colors, you have one particular type of matrix model graph. Now, you can decide to pick the red and black. That gives you another matrix model graph, completely different. And then you can decide to pick the black and green. That gives another one. And you have to consider all of this to understand the large N limit, the structure of the large N limit. It's very, it's both nice and sort of puzzling, because these lines might be very different. For example, here, red and green are UN, associated with UN, and the black are associated with OD. It's not so natural to consider red and black, but that's what you have to do.
No, my question is different. I thought you start from some Riemann surface, you put vertices, and then start connecting these vertices. No?
Why do you say I start with some Riemann surface?
Because you define G independent of the index of...
What G? Sorry, I think I didn't
in the
understand.
first slide, and you define G.
Here?
I can go back further.
Go further? Tell me, I stop.
Here, this H is G plus something.
Yes. So this is what I explained, that this is just related to the number of connected components. When you have several Riemann surfaces, then you have to take this into account. This is just because when you have multi-trace interactions, a connected Fineman graph may yield disconnected Riemann surfaces. Just because a vertex like this is one vertex, but because of the double trace structure, the ribbons do not mix up. So in terms of the Fineman graph, you would like to say that this has to be connected because this is one vertex. But in terms of the representation as Riemann surfaces of your graph, you might get two disconnected Riemann surfaces. And you have to take that into account. That's it. It's just a technical thing, well-known technical factor that you have to introduce for multi-trace matrix models. There's nothing very deep in that here. I can explain you in more details if you like.
Well, in your model, the Riemann surface is sometimes non-connected, or you always think the Riemann surface is one connected component?
They're not necessarily connected. For single trace matrix models, a connected Fineman graph is associated with a connected Riemann surface. For multi-trace matrix models, a connected Fineman graph is associated in general with multiply connected Riemann surfaces. That's just a fact of life that comes from this. And then you have to take that into account. That's how the factors of n work. Okay. It's not very deep. It's just the generalization of what everybody knows for single trace to the multi-trace case, which you need to take into account in this game, because in general, you will get this multi-trace thing. If you have maximally single trace models, then this never enters. All these corrections are always zero. That's the property of the maximally single trace models. Did I answer
Yeah.
your question? All right. So now let's go to physics. I will still talk about large and large data with the physics applications. So what I want to emphasize is this holographic description of black holes, which suggests, as I explained in the school, in a very general way, that quantum black holes should be equivalent to large and strongly coupled matrix quantum mechanical systems. The typical setup involves branes. You have branes, you have open strings that join the branes, and you have matrices because the open strings have two ends, and each of the index labels on which brane the open string end. So always variables xij. You always have also a third index, mu, which is just the rotation index for the directions that are transverse to your stacks of branes. This is completely generic, so you always get this sort of variables. Tensor models look very exotic from the point of view of string theory because of this picture. Strings have two endpoints, so they always give matrices. So a tensor model with free index, there's really no string variable here. You absolutely have no idea how to make the link with string theory. But of course, here, because you have this index mu, it's of different nature of the other one, I and j, but you have, in a natural way, objects with free indices. Okay? And that looks a bit like a tensor. Right? So that's what we can use when we're going to use. The index mu, so it transforms into this orthogonal group associated with the rotation transverse to the branes. And then the idea would be to take the large D limit and make the link with tensors. Okay. There's also, of course, when you do this, an immediate, at least philosophical relation with the work of M. Paran and collaborators, and also Nuala and collaborators, on the large dimension limit of general relativity. So because D is the number of transverse direction to the brain, so large D means a lot of space-time dimensions. So this, I know that Roberto is really thinking very seriously about the possible relation here, but for the moment it's at the level of idea and philosophy. I don't want to say anything more precise about this. The most important lesson of this point of view is to realize that melons, or generalized melons, are relevant for matrix models too. So not only relevant for tensor models, they're also relevant for matrix models when you do this large D limit. So my personal opinion is that this is actually why SYK is interesting. Melons are relevant and interesting for matrix models. And we know that then they have to be sort of relevant and interesting for black holes because they're related to matrix models. SYK also has a melonic structure, and thus sort of accidentally will also mimic the black holes. Of course, that's not the historical way of all how these developments were introduced. But I think that's a logical way. Right? And it's very strange that a disordered model like SYK could be related to black holes, but if you realize that the melonic structure is also relevant for matrix models, then it is natural that there will indeed be the link, albeit maybe accidental. Okay, so this is the kind of matrix models that we can do. The scaling I explained before here will be written in this way. It's a special case of the scaling we talked about before. And I repeat because it's so important, but I already said it before. Naively, this enhanced scaling seems impossible, okay, because you enhance compared to an ordinary vector model scaling. How can the large D limit still exist? But because the top scaling is so delicate, that's the intuition we have, and that was the question I had a few minutes ago. But there are these remarkable properties that the large D and large N limit will still exist. And in this context of matrix model with an index mu, the intuition is really that the power of D in a diagram is related to the number of OD loops that you can draw on the Riemann surface on which the matrix model graphs are drawn themselves, and the genus of the Riemann surface will constrain the number of ways you can draw loops on it. And so there is a non-trivial relationship between the powers of D that can enter and the powers of N. And so it's really this very intricate, very nice combination of vector model-like structure and matrix model-like structure, which allows to improve the ordinary vector model scaling and still have something consistent. Okay, so that's what I explained. So this is no enhancement. This guy will have a square root of D. That's what we call here genus 1/2. This guy will have a factor of the enhancement, etc., etc. Okay. The large N and large D limit works as follows. The large N limit is the usual one. Here it's just the genus because I'm using just single trace interactions. And then at each genus, you can expand. Oh, sorry. So this is D. This should not be N. This is D. You expand at large D, and you have this L, which is the index, essentially, of the graph here. One important feature is that the large D limit defined in this way, this enhanced large D, do not commute with the large N limit. Okay, I explained that in the school. I repeat it here because that's a crucial feature. It does not commute. If you consider the graphs with all possible genera, then you might have graphs that have arbitrary high power of D. So the large D limit would not exist. But if you first do large N, you restrict yourself to fixed genus, then the large D limit of the sum of graphs of fixed genus exists and is well defined. So that's a new expansion of the Fineman graph of fixed genus, in particular of planar graphs. You're getting this sort of peaks that we're used to. The big idea, I don't know how much is it true. It's partially true, at least. We know already it's partially true. I don't know how far we will be able to go with this idea. But the big idea seems to be that this new approximation of the sum of the planar graphs, albeit it's very simple at the end of the day. It's more complicated graphs maybe than what we're used to, but it's very simple yet. I mean, we can sum them up, write closed equations for them. They are simple. Albeit they are simple, it looks like they do capture correctly the qualitative physics associated with the full sum over the planar graphs. So this is the outstanding idea, new idea. That it seems that we're getting an approximation to the sum of the planar graphs, which, albeit simple, capture the physics associated with the full sum of the planar. If true, we can go very far, okay, with this idea. All right. So let's now discuss a particular model and the surprising new physics that we discovered in this particular model, which can be generalized in interesting ways in many directions. Keep, look at the archive over the coming weeks, and you'll have, I think, another paper. But this is the simplest instance, and it captures the essence of the idea. So this is a model of complex fermions, so the standard canonically quantized complex fermions. We are getting this nice non-melonic interaction terms to get generalized melons and leading graphs, and I'm adding a mass term for the fermions. Okay, I'm adding this mass term. What is the interpretation in terms of strings that you have? The mass term is just telling you that if you create a string by acting with this creation operator psi, which is a matrix, so it's a matrix that creates a string, its mass will be n. Now, in a model of this sort, you have two types of indices, the green and the red, because the symmetry group, as usual in tensor model, will be like UN cross UN. So I depicted here the green branes. This is, let's say, the first index A of the matrices. And the red branes is the second index B. Okay? Mu, as usual, should be interpreted as the transverse directions. Now, the strings are created by psi. So they always have a green index and a red index. Okay? So in this particular construction, it's sort of a particular type of branes that you're getting. The strings, you cannot have green, green, or red, red strings. You only have red, green strings. Okay? It's a special thing, but fine. So your strings go from green to red. And the mass parameter, capital M, so this should be capital M, sorry, it's a mistake, just is interpreted as the distance between the stack of branes, as usual. Because the mass of a string is proportional to its length. The proportionality would be some dimension full constant, the string length, or the string tension. So this mass parameter, geometrically, is like the distance between the green and the red branes. Now, since we don't have any green, green, or red, red strings in this particular setup, the stack of purely green or purely red branes is completely non-dynamical. So it would be like a defect in space-time, but it doesn't do anything. It doesn't interact with itself, it doesn't gravitate. It's just a defect, a geometrical defect. But the interactions are mediated by these open strings between red and green, so the red and green guys will behave when they're together as a normal stack of branes. Okay? So very simple model, and this is like the brane-like interpretation of it. Is that clear? All right. So the parameters, you have this mass, so the distance between the branes, the coupling, and the temperature. These are all dimensionful. So let's choose lambda equal 1, or consider these parameters in units of lambda. And I want to understand what the model is doing as function of the distance, the mass, and the temperature. How long do I have? I don't remember when I started.
You would have roughly 7 minutes.
7 minutes.
It's not a tight schedule.
Okay.
So
7, maybe plus 5 would be okay.
5.
Yeah. Okay. So, all right. So what can we understand in this Tm plane very easily? Yes?
Sorry, the size you had, are they really matrices or are they suppressed tensors?
The psi's are matrices.
Or purely matrices?
With the index mu.
Okay.
Okay, so you also have these transverse directions. All right. So this regime here is the very high temperature regime. Because it's a fermionic model, high temperature is always perturbative. It's the famous high temperature perturbative expansion in condensed matter systems of fermions that you can use. This is exactly the same sort of perturbation theory that you use in SYK as well. So you perturb around the zero Hamiltonian and around the state which has maximal entropy. But for fermion system, that's well defined. You can perturb around zero Hamiltonian at very high temperature. Okay, so this is the usual, well, not so usual maybe for particle theorists, but well known for condensed matter theorists, high temperature expansion. And so the model will be perturbative, whatever, as soon as the temperature is large. There's another regime that you may want to contemplate, which is fixed temperature, but very large mass, very large distance between the branes. In that case, clearly, the strings are very little excited because they're so massive. And this will yield the standard perturbative expansion, where you have very few excitations that you have to take into account. This is the textbook in high energy physics, not in condensed matter, but in condensed matter they have both. In standard QFT textbook, you only have this sort of perturbative expansion that is discussed in general. It's the large mass, so you're going to use just the standard propagator for the fermion, completely ordinary perturbation theory around a model which is just the harmonic oscillator. So in this regime, the leading terms is just the fermionic harmonic oscillator, and the interaction psi to the fourth term is a very small perturbation. And you treat it in the normal perturbative way. Okay, so you have this other perturbation. So in some sense, in this model, the effective coupling constant is the minimum of these two numbers, 1 over m and 1 over t. Because when m is large, you're perturbative. When t is large, you're perturbative. Okay, so you have this. And in the Euclidean formulation, this gives sort of the minimal mass of the Matsubara modes of your fields. Okay, so you have, because they're fermions, they have a thermal mass, and they also have the explicit mass. And it's the lowest will give the non-perturbative contribution, the highest will give the perturbative contribution. So that's what happens. All right. So all this region is perturbative. There should be no problem to treat the model in this region here. So for example, if you compute the entropy along this line, or anywhere actually at very high temperature, H is 0, so it's a super high temperature. It means that all the fermions are excited. Well, per degrees of freedom, the entropy will be just log 2. There's no mystery here. It's the entropy of this maximally entropic state, log 2 per fermionic degrees of freedom. And then you perturb, and you have a perturbative expansion. Here, the same. Here you perturb around the harmonic oscillator. So if, in particular, if you're at 0 temperature, the vacuum is just the Fock vacuum, and the entropy is 0. Completely trivial. 0 temperature entropy, you have only one vacuum, and if you're at finite temperature, you perturb around the thermal harmonic oscillator. There's nothing very fancy here, and you can do that. Okay. Now, you can consider this regime here. 0 mass, but you lower the temperature. Then the model I have here, essentially the math match essentially exactly the math of the SYK model. So when n is 0, I can, with little changes, use all what is known about the SYK model to do the math. And so I will compute and realize that when I go to very low temperature, I have all these nice features of non-zero temperature entropy. So, and you can compute it in this model. It's Catalan number divided by pi plus 1 for log 2. So, you know, here we started at very high temperature. This is the 0 temperature. It's analytic. And in the middle, you can do numerics, but it's well known. And at very small temperature, you get these beautiful scaling laws and all these properties that I have that you know very well. So no mystery here. It's the SYK physics. So going from here to there is not mysterious. It's SYK. What is strange is going from the right-hand side to the strong coupling. So starting not from the high temperature perturbation theory and reasoning, starting from the ordinary perturbation theory and reasoning. This is puzzling because, okay, here, for example, you have zero temperature entropy, and here we have non-zero temperature entropy. Something must happen here, very drastic. Nothing drastic happens when you go from here to there, but something drastic must happen when you go from here to there. So this was the puzzle that, from which we started to think about this problem. We wanted to understand what could happen. So the physics, if you have the brain picture in mind, is actually maybe quite intuitive. You start with very large mass. The two stacks of brains are super far away. Very few open strings are excited. Essentially, they don't interact, or very little. And then the mass is decreased and decreased. Well, you may expect that below some critical distance, there will be a gravitational collapse of the stack of brains. Isn't that natural? This seems to be like a toy model, but physically very similar to the idea you have matter that you squeeze and squeeze and squeeze. The distance is decreased. And, well, if we really believe that all these models can describe black holes, well, it's sort of natural that below some critical mass, you can create a black hole. You have the gravitational collapse. And if you create a black hole, you create a horizon, you create a macroscopic entropy. So when the system is not gravitationally collapsed, brains are very far away, there's no horizon, the entropy is 0. But as soon as there is a gravitational collapse, there is a macroscopic horizon, the system should have a macroscopic entropy. Yes?
Sorry, I mean, I tend to think of brains as black holes on their own, right, on the gravity side. I mean,
So here, it's not what happens because of the special properties of the model that you don't have green strings. So these guys are completely non-dynamical. In a more realistic model of this sort, which we can do, but I will not talk about it today, this would be the merging of two black holes. But in this model, because it's so special that only the green, red strings exist, this is not dynamical, so it has zero and it has nothing, it has no dynamics.
Is this something you can engineer in string theory somehow?
I don't know. This is the natural brain-like interpretation of the model I have. It would be very interesting to see if we can engineer this kind of simple sort of deep brain system in string theory with these properties. I don't know. I am not aware of any similar things.
But in this model, you expect some kind of phase transition, while in matrix model, you expect similar but not really to phase transition, some crossover.
So we are actually going to find the phase transition.
Oh.
So that's the main result.
Do you expect some similar, I don't know, crossover or something in matrix model as well?
Sure, and we're going to find not a crossover, we're going to find a phase transition.
Yeah, in this case, yeah.
In this case, but I think it will be very general. This is very,
But
simple.
mechanism itself intuitively is the same in matrix model.
Yeah. Well, that's a matrix model.
What if you're using not the complex fermion, but the Majorana fermion?
Sorry?
You start with the complex fermion.
Yeah.
So what if you can probably start with the Majorana fermion?
With Majorana fermion, so you cannot add mass.
Yeah.
Okay, so that's why we wanted to have the complex fermions. Or you have to have two sets of Majorana fermions, more complicated. But then it's like a complex fermion. All right. So let me give you results. All right. So as usual, you have to solve some Schwinger-Dyson equations. The new, which was a known feature that will allow to understand this phase diagram, is this. It turns out that for some values of the parameters that I will explicitly depict in the next slide, these equations can actually have two inequivalent solutions with all the correct physical properties, meaning that in particular in the UV, they match because this model is asymptotically free. Only solution in the UV must match by asymptotic free. But it turns out, that's the sort of the big surprise. It's a surprise from the point of view of these equations, probably not from the point of view of the discussion we've already had. But it's a surprise from the point of view of this equation that was not known. They can have two different solutions, inequivalent solutions for G, sigma, etc. Two different solutions with different physics, matching in the UV but completely different in the IR. And that we have completely proven with very detailed numerical analysis. And at the end of the day, this is what we find for the Tn plane, the phase diagram. Okay.
I'm sorry, which solution corresponds to the path integral? To the path integral.
So let me tell you. You're going to have the answer just now on this slide. If this wants to work. Okay, yeah. All right. So for this region of parameter, you have one solution which I call perturbative. It's not really perturbative because we've resummed all these graphs, but it's continuously deformed from the perturbative solution that you get at very large mass. Okay? So very large mass matches with the ordinary perturbation theory and it gets deformed, but you can follow continuously the solution. There's no mystery here. This solution exists till you cross this dashed line. So this dashed line tells you that on the right the solution exists, on the left it no longer exists. It's no longer a solution of the equation. Similarly, in this region of parameters you have another solution which is, I call black hole solution, SYK-like solution. It's the one which when you go to zero temperature will display the power law behavior and so on and so forth. So the non-zero, zero temperature entropy, the usual SYK physics. It exists here up to this other dashed line. That's what represents this dashed line. So in the middle, all this region is a region where coexist the two solutions to the equations. Outside, there's only one, but in this region, you have the two solutions of the Schrödinger-Dyson equation. Now, which one is relevant? So maybe that's your question. Well, you have to compute, as usual, you have to compute the free energy of the two. And the one with lowest free energy is dominating the path engine. And this thick black line here is the line where the free energies coincide. On the right-hand side of this black thick line, it's the perturbative solution that has less free energy. On the left-hand side, it is the SYK black hole-like solution. And so here we're describing a first-order phase transition between two different saddles, if you like, of UO model. And the entropy, so if you're at zero temperature, the entropy here would be strictly zero, and here it becomes macroscopic. First-order phase transition. And this happens, you know, all the way here. And then the last surprise that we found is that this line of first-order phase transition actually ends at the point where the two black hole-like and perturbative-like saddles match. So it's a critical point, very similar to the critical point in the liquid gas phase diagram for water, where, you know, in water you have liquid and gas, but then the transition ends at a critical point, which means that there's no genuine difference actually between liquid and gas. This is exactly similar. So we have a new critical point, something I have never seen before. I will finish by describing very quickly its main properties. It's in quantum mechanics, critical point with with non-trivial critical exponents, etc., etc. And that's at non-zero temperature, so it's not a quantum critical point. It's something, to me, completely new that I still don't fully understand, but we have the numerics very precise here. So in particular, if you start here from non-black hole phase, go to very high temperature, then you can actually smoothly go to the black hole. So you heat up your system enormously. In some sense, by heating up, you excite the strings. It's some sort of phase, you know, where you cannot distinguish black hole and non-black hole and go smoothly to the black hole. But if you are at low temperature, you have to go through this first-order phase transition. So that's a very interesting, and for gravity, it will be very interesting to understand the full detail of this in gravity. So just to finish, this is my last slide. This is an example of a quantity that we computed near the critical point. This is the heat capacity. And you have these divergences which are power law with very non-trivial critical exponents. Okay, so it's a strongly coupled interacting critical point that we found in this quantum mechanics, large N quantum mechanics. Another remarkable feature is that the critical exponents are asymmetric. They are not the same whether you go to the critical point from, for example, low temperature or high temperature. This is very unlike most of the critical points that we know. All the critical points that are describable by the renormalization group in the local field theory will have symmetric critical exponents. This is something you can derive from the scaling laws that you get with the renormalization group. Here, you don't have this property, so this sort of phenomena were known, they are very exotic, but this is the first explicit example I know of. People have discussed it in the condensed matter literature as some very abstract possibility in this, when you don't have a local QFT. But here we have an example. So there are a lot of mysteries here, I think, that I would like to understand. All right, I think it's enough. The slides here, I have 2 slides for bosons, but I think, yeah, we can stop. Thank you.
Any further questions for Frank?
Yes.
So I'm not sure about your interpretation, because for the ordinary SYK model with Majorana fermions with zero mass,
Yeah.
For such a model, we still also have 2 saddle point solutions, and usually one of them is suppressed by 1/n.
What do you mean? So what I mean is, no, I mean in the ordinary SYK, you have the saddle point equation. There's only one solution.
No, you have 2.
No. What do you mean surprised by 1/n? So the saddle point equations are equations that govern the
So
leading large n limit.
So for example, let's say Q equal 2 case.
Q equal 2 is forget it, because that's trivial special case.
Well,
a lot of trivial special properties.
But the structure is almost the same. You can
No, because you don't have black holes. You don't have.
But
It's only the zero. Here you only have a zero entropy phase. So Q equal 2 is special. I don't want to talk about it because it's really qualitatively different.
Saddle solutions still you can.
But there is some study by the Beatty transition as YK that there is various type of the Beatty transition. Like some people consider this Q equal 2 and Q equal 4 together. And
Yes, I know these things. Yeah.
Lattice, so
Yeah, they are very different. They have nothing to do with what I'm talking about here. So it's not like they have two solutions of a given set of Schwinger-Dyson equation. I know very well what you're talking about, but this is completely unrelated, both physically and mathematically, to what I explained. We can, if you like, we can dig more. I can explain more. But this is very, very different. Here, what I'm saying is that a given set of Schwinger-Dyson equation for given parameters have two solutions with the correct UV behavior. This you don't have in SYK or other cases. Even for Q equal 2, actually. So the Q equal 2 SYK, the Schwinger-Dyson equation is quadratic. So you have two roots, but only one has the correct UV behavior. So for Q equal 2 SYK also you have, there it's very easy to see that you have only one solution. This is very surprising to have two solutions from the math. From the physics, I think it's not so surprising because we understood that you had these two different regimes, large mass on the one hand, high temperature on the other hand. That seems inconsistent, but they have sort of to come together, and that's why you need two solutions.
And do you consider like the rank 3 tensor or matrix adding with some additional index? But the SYK model, you consider the large Q limit and they give some interesting. Is it here maybe higher length?
So large Q, that's something we've tried. We're still working. Actually, to start again. This. So if you can have a large Q generalization of this story. This will happen. This will be in the paper that we will publish in March and so on. But what happens is that all these guys, all this interesting structure, scales to 0 when Q is large. And it scales to 0 exponentially fast at large Q. So for this sort of thing, the large Q limit seems to be trivial in a sense. Because at leading order, you don't find it. So this is shrink. So this is like Q equal 4, but you can do Q equal 6, then it will be here, and Q equal 8, etc. And very soon, you don't see anything. So the large Q, we hoped actually it would be a nice way to study properties of the critical point, for example, at large Q. That seems, I'm not sure 100% yet because I want to understand a bit better, but it seems that it's not going to work because everything scales exponentially to 0 at large Q. We have other ideas to study these critical points analytically. It would be more to generalize this one-dimensional model to 1 plus epsilon dimension, or 2 minus epsilon dimension. And then the model should still have this structure, and maybe in the epsilon expansion, then we can do something. Because you can show that in 2 minus epsilon dimension, this is weakly coupled. So this is an idea that is on the table. We didn't have time to push it very far, but we could do it. But that seems more promising than large Q, as far as I understand.
Thanks again.